All right, so our topic is the introduction to hypothesis testing. In hypothesis testing, you're going to find a lot of overlap with what you just learned in terms of creating confidence intervals. Because with a hypothesis test, what we're going to do instead, you remember with those confidence intervals, as you went and you got a test, you got a point estimate that you use to build your confidence interval around. Well, what if that point estimate was no good, or what if the parameter itself has changed? More so, what if the parameter has changed? So for instance, we've thought all along that, well, let's go with the temperature, the mean body temperature. Let's say that for years and years, we've accepted 98.6 to be the mean body temperature. But hospitals are starting to question that, and they're no longer, they're wondering, maybe something has changed or something to do with our lifestyle, or who knows what. So that's one example. So what they can do is take this very large, they can take a very large sample and create the statistic. In this case, it would be a mean. And then they can test whether or not the accepted value of 98.6 is still valid based on how far off that mean that they got from the sample statistic is from the accepted value. So it's, in other words, is it really possible that this is what we think it is, given that we took this huge sample and it was way off the mark? Better example of something that is definitely more dynamic is, say, the proportion of the population that has landlines in their home. A lot of people are ditching the landlines, and just because they're always using their cell phone, it's kind of redundant to have a landline. Well, that wasn't the case as much 15 years ago, and it's just slowly kind of leveling off. I'm trying to do a little graph here. It's leveling off. And so the proportion of the population that has landlines now is much smaller than it was 15 years ago. So the accepted norm, they have to recalibrate and decide what's an estimate for the new parameter. So hypothesis testing is a formalized way to do it. Formality is important in statistics and in science in general. So we got to formalize the process so that when we pass on the data to other people involved, they know exactly what we mean when we say this or that. So we're going to learn the formal language of this concept of hypothesis testing. Okay, so let's cruise on here. There's two parts to a hypothesis test, so it's pretty simple. One's called the null, and the other is called the alternative hypothesis. And it's basically, the idea is the null hypothesis says this is what the status quo or accepted value of this parameter has been thus far. And then the alternative hypothesis is going to say, do we think it's increased? Do we think it's decreased? Or in a more generic sense, do we think it's just changed, which means it could have done either? And then we'll look at, if we got a bad sample, we can run into errors, and we'll use an alpha again that we attach to how certain we are. So alpha is going to come into play again. And if you really look at this, like I said, you can see the relationship this has with the idea of a confidence interval. And then we're going to state the conclusions of our hypothesis test. So a formalized way to state our conclusion, so it's all understandable in the community. Okay, so the hypothesis is the statement that might be regarding a proportion or a mean or a standard deviation. Those are the three parameters we're going to consider in our hypothesis tests. And just to give you an example, Okay, so we use H naught to represent the null hypothesis. Okay, so our null hypothesis could say that the population mean is equal to 98.6. Okay, so that's the status quo we're testing against. And our alternative hypothesis, we just put subscript with a 1. So subscript 0 is null hypothesis. And subscript 1 is the alternative. And it could be one of 3 things. We could say that we now think that it's less than the status quo, 98.6. Or it can only take on one of these 3 things, but I'm going to write down. We might say, oh, it's gotten higher. Or we might just say it's no longer. So we just use the not equal to 98.6, and we're not going to commit to whether we think it's less than. Okay, so this would be possible alternative hypotheses. Okay, so this is kind of the language in a nutshell and the symbology. So let's look at this example, claims regarding volunteer time of the population. So in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this is different today. Okay, so they didn't say that they believes that it's larger. Had a quicker way to, keeps taking away my pen. So so he didn't say larger or smaller, he just said different. So of my 3 options, we're talking about not equal to. Okay, so let's go ahead and put down H naught is going to be that. Now the parameter in question is, this is a percentage of the population, so this is proportion. So P. So H naught is the status quo that we're testing against, was the 62%. And H1 is, this is different. This has changed. Well, all we can glean from that is not equal to 0.62. So this is what we're going to learn how to go test. Mostly today, we're just going to learn how to set things up and get the language down. So we're going to kind of ease into this process. Okay, so null hypothesis is that the parameter equals the status quo, and the alternative hypothesis, it could be greater than, and we have names for those, so we'll get to that in a minute. This is not equal to. So let's look at another one. Okay, so this time, according to a study published in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes. Now, this is something that could be quite dynamic because all the cell phone companies are offering all these different plans, and so as the new plans kick in, people might be willing to not pay attention as much to how long their calls are and not worry about it. And this could increase. So a researcher believes that the mean length has increased since then. So what's the parameter in question? Well, that's a giveaway right there. This is mu, the mean, population mean. What's the null hypothesis? H naught, we're testing against the belief that the mean length is 3.25, so we're going to say mu equals 3.25. What's the alternative hypothesis? This time we've committed to a direction here. The researcher thinks it's increased, so that implies that now we believe mu is greater than 3.25. Okay, so again, we're just translating a situation into the formal language of hypothesis tests in symbology. Here's another one, different parameter. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. Okay, so what they've got is they've got this situation where they would like to be very consistent about the amount of wine that goes in their bottles that they send out. So obviously, if we can decrease something that represents standard deviation, which represents dispersion, or if we can decrease that, then of course it's going to be more consistent. So this time, sigma, the population standard deviation, is at play. Null hypothesis is the status quo, what we're used to it being, and what we're testing is that we think that this new equipment brings the variation down. Okay, so we've hit all three parameters that we're going to be looking at: proportion, mean, standard deviation. So I wonder what would happen if I try to slide this way. Nope. Okay, so we're going to base our hypothesis test on sample evidence and then probability. And we can break this down. Let me also, before we get going, when we do like parameter greater than value, if this is our H1, we call this a right-tailed test. And the reason for that is here's our normal curve, here's the mean or we're testing against, and if it's increased, well then it's moved over here somewhere into the right tail. So this would be why we're using right tail. So if it's greater, then it pushes it over into the right tail. If our H1 says parameter less than value, we would call it left tail. Okay, so now it's somewhere over here in the left tail. And lastly, if H1 says just plain old not equal to, then it could be on either side, so we call this two-tailed. Two-tailed testing. Okay, and if we split the value between both tails, we're going to see that we have to divide alpha in half. We haven't met alpha yet, but when we get there, when we do a two-tailed test, we'll have to split the alpha and allocate half of it to one side and half of it to the other side. If we do a right-tailed or left-tailed, the entire alpha part is going to get to go to one side. Okay, this just repeats that idea that H naught represents the null hypothesis. Here's an example, yet another one. So this is for a population proportion again. So the proportion of female college students used to be 0.41. I know for sure that's no longer, that can't be right anymore, because most, well, my experience is most of my classes are the other way around. There are more females in the class than there are males. And we suspect that the population proportion has increased. And so our formal description of this is going to be, status quo is that the proportion is 0.41. The alternative is that it's increased. And here's just a general rundown. As I described, the two-tailed test is the not equal, and the left-tailed test is when it's less than, and the right-tailed test is greater than. Okay, so as you can see, the H naught is always an equals, parameter equals some value, status quo, and then the rest depends. Okay, so go ahead and look these over. We already did these. Okay, so this is a repeat of what was up front. So lots of duplicate information here. Okay, so once we've done our testing, we either reject the null hypothesis or we do not reject the null hypothesis. So our formal language is going to be, we reject or we do not reject at some level of significance, which is tied to alpha. So it's kind of similar to that idea that we're 95% certain that the actual population proportion is between low limit, high limit when we did the last section. Okay. If there's two kinds of errors that we can run into, we call it type 1 error and type 2 error. So a type 2 error occurs when we reject H naught, but in the population, H naught is actually still true. So type 1 error, you reject null hypothesis, but it's still true. And if our data indicates that we don't reject the null hypothesis, but actually the alternative hypothesis is true, then that's a type 2 error. Okay, so it's kind of like you have to consult these a lot. If you're asked questions about it, you might have to reconsult. It's kind of like daylight saving time. It's like, did I lose sleep or gain sleep? Okay, so in 2008, 62% of American adults regularly volunteered their time for charity work. The researcher believes that this percentage is different today. What would it mean to make a type 1 error? Well, a type 1 error would be that the data you got said that yes, it's changed, but in essence, it's really still at about 62%. So that was type 1 is we rejected the null hypothesis, but it's actually still true. So for the type 2 error in this scenario, that would be, so if we're going to not reject the null hypothesis, then we our data tells us that there's not enough evidence to conclude that it's changed from 62, but in actuality, it has changed. So that would be the type 2 error. Okay. So I'm going to let you think about how that would pertain to part B here. Go ahead and look that over and come up with a commitment. All right, so here's your solutions here for part B. Self-check. Okay, we're not going to really get the opportunity today to dig into the fun of actually following through on all this. Again, all we're doing is learning the language and the process, and then we'll dig into the details on Wednesday. Okay, again, type 1 error. The sample says it's changed, but it hasn't. Type 2 error, the sample tells us that it hasn't changed, but it actually has. So really both result from, you know, a bad sample. So how can we try and minimize one or both of these errors? Okay, I told you we'd be talking about alpha. Now, alpha technically represents the probability of a type 1 error. But it's very analogous to the alpha that you used for your confidence intervals. It just so happens that in this scenario, alpha represents the probability of what we call the type 1 error. Beta is the symbol used to represent the probability of a type 2 error. Okay, we don't have to overthink that so much. Just know that we're going to be working with an alpha and it's going to be established on our behalf. Okay, so the probability of a type 1 error is determined by the researcher. So we call that the level of significance. So could be 0.05 or you know, similar to the alphas that we worked with last section. Okay. Here's something interesting. If we increase the probability of a type 1 error, then the type 2 error is less likely. So they're kind of inversely proportional. And we don't use the word accept. You'll see that there's an accepted lingo, and accepting the null hypothesis is not how we use it. We basically just say that we do not reject. So there's evidence to conclude we do not reject. Okay. So we want to learn how to word this if we've done our testing and these are the results that occurred. So this is according to a study, the mean length of a phone call on a cellular phone was 3.25 minutes. Researcher believes the mean length of the call has grown or increased since then. So suppose the sample evidence indicated that the null hypothesis should be rejected. How are we going to word that? And then for part B, let's go the other way around. Suppose the sample evidence indicated that the null hypothesis should not be rejected. How are we going to word that? So remember, we're wording it this way so that when we pass it on to our colleagues, they've got the formalized conclusion and there's no ambiguity about what the heck happened. Okay, so we're going to say that the null hypothesis is rejected. We would say there is sufficient evidence to conclude that the mean length of the phone call on a cell phone is greater than 3.25 minutes. Now what's missing here is what level of significance. So we're going to need to tie alpha into this statement at some point. So it would change it by saying that there is evidence at the alpha equals 0.05 level of significance to conclude that the mean length of a phone call on a cell phone is now greater than 3.25 minutes. And if we went the other way around, we're going to say yeah, these are not the best wording I've ever seen. Let me pull up a slightly different example and then Okay, so something I'll be distributing to you a little later is this PDF. And it's kind of nice because it bundles everything together into one concise package. And it includes the statement regarding the test. So once we get done, we're going to basically fill in the blanks here. And we're going to say there is, use one of these two depending on the results. So there is or there is not sufficient evidence at the alpha equals, and that depends on what we're given for alpha, level of significance to conclude that statement regarding the parameter is something like what we said about the mean length of a phone call is no longer 0.63 or whatever, 0.63. That was the proportion. But okay, so this is kind of more formal. We're just going to substitute whatever differs from one test to the next. And then here's a few of the tests that we'll be looking at, but don't have to worry about that just yet. Okay, so really I'm just going to give you a fairly brief online assignment that with the whole goal just being that you exercise the concepts that we've that I've been discussing here. And I'll go ahead and make sure you've got access to these slides if you want to refer back to them. And yeah, so I don't, you're just going to be deciding what kind of test, if it's a right-tailed, left-tailed, two-tailed, you're going to be setting up the null and the alternative hypotheses, deciding which parameter is being tested. So basically it's just kind of putting your toes or foot in the water, and then we'll dive in on Wednesday. So we got through pretty early today, so that leaves plenty of time if you have any questions.